and welcome Mindsetters to this session of grade 11 maths learn extra live. I hope you guys are ready. You've got your pens and pads out and you're excited as I am, and you're gonna make some notes. Guys, I cannot stress enough, make sure you've got a pen and pad near you and make some notes. It's so important. And today, what are we actually going to be covering today?
Hi everybody, we're going to be doing some trigonometry, especially those tough concepts around equations, so stay tuned for trig equations.
All right, so on that note, while you go across through
Thank
there,
you.
I'm going to tell the Mindsetters, make sure you get on the page and get chatting to us. Make sure that you do not forget that I still have to give away these Casio calculators and this awesome labeler. So make sure you guys are on the page and chatting, so I can see that you guys are participating with us in today's session. But make sure, Mindsetters, that you keep talking to each other, share notes, and also, I just want to send a quick shout out to Liberty. Thank you for sponsoring the show. So, I think we're almost good to go. We are?
Yeah.
All right. So, on that note, take it away.
Welcome everybody again, it's trig equations time, and we're going to do some theory and then hopefully do some practice examples of the type of questions you'll be seeing when you actually get to the exams. So let's do a little bit of theory first. If you are asked to solve a trig equation, you often are asked to work out what the general solution is. And that is because when we saw last week, when we drew the trig graphs or the trig functions, we found that because each curve is cyclical, or because each curve is periodic over a certain number of degrees, that for every value that cos has within its range of -1 to 1, we're going to find a multitude, or multiple values for possible angles. So that means that when I'm asking for a specific, or I'm trying to solve for a specific angle, I'm never ever going to just get one. I'm going to get a multiple set if I don't have a domain. If I do have a domain, then I'm going to be working within that domain. So you'll often find in grade 11 you're asked for the general solution, not just the solution because there isn't one or two, but because there is a formula that we're going to extract that actually gives us all the possibilities. So with the periodic nature of the curves comes this unique section of maths that has a general solution. So you wouldn't have a general solution, for example, in algebra, or maybe you do if you've got an inequality, you would have kind of a general answer, but not a solution as such, where we could actually extract those values. So let's look at some of the theory. If you are asked, for example, to solve for sine theta equals a half, then if we drew a very rough sketch of what my function looks like, we would have these cycles of maxima and minima of 1. So if we were trying to solve for when sine theta is a half, just look at how many possibilities there are. We'd have this possibility, that one, this one, that one, this one, that one. And we can see that if I get this one, for example, this possibility here, that it's going to repeat itself over there, and it's going to repeat itself over there, it's going to repeat itself over there, and until infinity. So we're going to have all these purple solutions. At the same time, we're going to have this solution, that one there, that one there, that one there, that one there. So we have all those possible blue solutions as well. So whenever you're trying to solve for theta, you cannot just write one value. Now you'll find that your calculator, because it's limited, it only gives you one value. And what we need to identify is what value does the calculator give us so that we can then find our second solution. So does the calculator give us the cross or give us the purple dot? And once we've got one of those, we can actually work out the second one. And in that way, we are saying we are getting all the solutions, all the multiple solutions in that set, and obviously to infinity as well. So if sine theta is equal to a half, then we're actually saying that theta is going to be equal to my purple solutions, and theta is also equal to my blue solutions. And I said the calculator would only give you one, so let's have a look at what the calculator gives us. First of all, we're in to the -1 mode, and we'd like to find out what is the angle that gives us a ratio of 0.5, and that gives us 30 degrees. So again, calculator is limited, gives you 30, doesn't actually give you a degree, but we are working in degrees. Okay, so the purple ones are 30 degrees. And it gave us one possible value, which we are saying would be this value over here. So what would this purple one here be, and what would that purple one there be? How would we be able to write that one? Well, it would just be 360 degrees later. So we'd have 360 degrees later. And then the second one here would be another 360 degrees, and we'd carry on like that to infinity. So we say that it can be written as multiples of 360, where k is going to be an integer, because I can also go back and get this one as a minus 360 and that as minus 720. So this is what we refer to as the general solution. It is a little formula that is able to tell you every single possibility of that sine ratio to be a half. Now, we also get the second set, which was our blue set, and that blue set would be that value over here, which we can see that the maximum would happen at 90. So this angle is happening between 90 and 180, and it's actually in the second quadrant. So that would be 180 minus that calculator angle, and that would be our second angle of 150. So the blue ones would be 150 degrees, and they're also periodic, so it would be 360. So in this way, k would still be an element of the integers. So in this way, if we had to do it in general, or set up a general solution, if I have sine theta equals p, for example, then theta will always be what I call the calculator angle, because it only gives you 1, plus k360, or theta will be equal to 180 degrees minus the calculator angle plus k360. So we would have two separate formulae, one giving us the purples, one giving us the blues. And that would be the sine ratio. Okay, what would happen if we had cos theta equals a half? What does the graph look like then? Well, this time around it starts at 1 and it goes down to minus 1 and it keeps on doing these curves. The same thing here. So it's still also 1 minus 1. And all we need to know is what does the calculator give us if we have a cos of 0.5. This time around it gives us 60 degrees. So we'd have 60 degrees to give us this first one. So that would be my 60 degrees, and then I would get it again there, and I would get it again there, and I would get it over here and over there. So my blue ones this time would be this angle here, that one there, that one there, that one there, etc. Now, the calculator has given us 60, it's given us this one, but can you see that we have this value here is symmetrical to that one there? So if I say that this one's 60 over here, it must mean that the minus 60 is over here. And with the cos function, I actually don't need a second calculation. All I need to do is to take the calculator angle, and I need to then take the additive inverse of it, which is really great. So our thetas that are purple would be 60 degrees plus k360, and our blue ones, we don't even have to think about it, because cos is symmetrical about the y-axis, would be minus 60 plus k360. And in this way, every single possible solution is captured where k is an element of the integers. So if we were looking at a general solution for cos theta equals p, then we'd have theta is actually just equal to plus or minus what the calculator gives us plus k360. Calculator, where k is an element of the integers. So as with sine, we needed to utilize that difference between 180 and the calculator angle. This time round, we can just use plus or minus, which is really, really nice. And then the tan function is even easier, because if I say to you that tan theta equals 1, my tan function is periodic over 180 degrees. So what happens is at 90 degrees I get an asymptote, and then I get these I get these curves doing that, and then doing that, and doing that. So if I'm asking you for where is it equal to 1, it would be equal to 1 there, and the second one is just 180 degrees later, because the tan function is periodic over 180. So tan, there's no calculation. It's whatever the calculator gives you, which in this case is 45, plus, and its period is 180. So one solution only for tan. We don't have to think about it. There are no intermittent ones over here that we need to go and find. So therefore, we can capture every single solution with one formula, and that is its general solution. Well, I think that gives us a little bit of background how to integrate the solving of equations with the graphs that we did last week. So let's go to some examples. Okay, so consider the equation 2 cos A plus 40 degrees is equal to negative 0,639, where A is in between negative 360 to 0. Now, the first thing that you would do is you wouldn't take cognizance of that domain. You would ignore it to start off with while you work out what the general solution is. Once you've got the general solution, then you'll come back and insert the various k values that would actually give you the finite number of solutions within a particular domain. So if I take you back to where we were, this general solution over here for cos, if I asked you to work between, let's say we were working between here and let's say there, and I said only values between there and there, well, that is 270 degrees, and that would be 360 plus another 180, so that would be minus 540. So I would then say to you, please give me solutions, and let's say, yeah, let's give solutions for cos theta equals a half between negative 540 and 270, and you would then say it would be these two, because that's when k is 0. But then from this one, I'm going to minus 360 to get this one. And with this one, I'm going to minus 360 to get that one. So in this set, I'm getting 4 by substituting relevant k values that will give me values that are sitting in the given domain. But can you see how you first write down your general solution in order to then go and pick what values you require for those specific k values? Right, so let's go back there. Okay, so even though we're given this domain, we will not use it straight away. We will first find the general solution on 2 cos of A 40 degrees. So solving for A would mean that we've got 2 cos of A plus 40 degrees is equal to negative 0,639. Now again, when we worked with the sine theta, cos theta earlier, your trig ratio has to be in its, well, it's got to be the subject of the formula, basically. So if you've got any terms or any coefficients that cos ratio may be attached to, we need to solve for that ratio first before we can actually use the calculator. So if we look at our equation over here, we've actually got that there's a coefficient of 2. We've got to get that coefficient to be 1. We have got this bracket, but this bracket belongs together. That 40 degrees is not a term. It's not a ratio term. It's actually theta plus 40 degrees. So we cannot take the 40 over to the other side because that's degrees, that's ratio. They're not like quantities. This belongs as part of the angle. That belongs as part of the ratio, so the two don't go together. So that stays, but this coefficient of 2 must go. So if I have 2 times cos, I'm going to be left with cos of A plus 40 is equal to negative 0,639, and I'm going to divide it by 2. Okay, and once I've got that, Now I can go to the calculator and see what value should the calculator give me. Now notice that cos is negative. So when we had our first theory, we looked at a cos that had a positive ratio. So for example, I gave you positive a half, and it gave us all of those. Now if I took a negative a half, what would the calculator give me as first? The calculator is going to give me this obtuse angle, this angle that's off to 90 degrees. That's what the calculator is going to give me. But the other one is going to be this value over here. So it's still symmetric to that obtuse angle. So you need to preempt. What should the calculator be giving me? Am I happy with that kind of value? Does it make sense? Okay, so we go back there. And we've got a negative ratio. What are we expecting the calculator to give us? Because calculator is only a machine that you're putting stuff into. It's giving you some stuff out, but you need to be able to engage with that kind of answer that the calculator is giving you to see, am I doing the right thing here? So negative ratio means the angle's obtuse. So what you're going to have is, firstly, you're going to have a positive obtuse angle, and then you're going to get a negative obtuse angle. So we're going to get an A plus 40 degrees. That's equal to the calculator angle. And then we're going to get those multiples of 360. Or A plus 40 degrees is going to be equal to the additive inverse plus K360. Where do we get that from? Because the cos function is symmetrical. So we forget the one, the additive inverse of the other. Okay, and now we're going to go to the calculator. And we need this negative 0.639 that we're going to divide by 2. And we're getting, can you see 108,6? So we are getting the obtuse angle that we expected, that we predicted that we were going to get. We just didn't know how big, but there it is, 108,6. Have a look at the decimals, 0.632687. You're not going to write them all down. You're only going to write one of them with a little dot to indicate that you're not rounding off yet. You only round off in your final one, okay? And let's remember that, 108,63.
Oh, all you have to do is just, in that corner there, there's that little X there, far right,
No,
on the main screen.
This one.
Yes, that's the one. There we go.
Thank you.
Oh,
Okay.
it's back.
All right, we'll take a break. We'll come
Okay,
back.
no problem. So mindsetters, do not disappear. We're going to be right back after this break. Stay tuned.